Thank you everyone again for joining our second webinar of this afternoon. Our speaker is Professor Jyh-Ching of National Tsinghua University. Professor Juang will be presenting to us on the Phoenix CubeSat accomplishments and lessons learned. Professor Juang, please go ahead.
Thank you, and good afternoon, good evening, good morning to everybody. Okay, so I would like to share with you some of our past experience on the Phoenix CubeSat. As we know, the CubeSat is a many important subject, which is the main focus on this series of lecture, and I would like to share my part, talk about what we have done, and then what we have endured in this process, so that hopefully that's okay, can encourage everyone. Okay, so brief introduction of myself. I'm Jyh-Ching Juang, a professor from the Department of Electrical Engineering, National Tsinghua University, and my association with satellite, I was a principal investigator of the Phoenix CubeSat, which is a CubeSat that's developed and manufactured, launched, and operated in Taiwan. And currently, I'm also responsible for the payload development of the national Taiwan's Triton mission for the GNSS reflectometer mission. And also, I also serve as a regional coordinator of the UNISEC Taiwan. So that means I have been involved with some satellite and CubeSat related activity in Taiwan. And as we have known, I think this should be familiar to most of you. But I try to put this into a historical perspective. The arrival of a CubeSat it's at the turn of the century. That's around 2000 or 1999, and it's been initiated by Baptiste and Jody, and that has been set up the standard. And this, because a nice form factor, because all the ICT technology have been involved in this kind of design, so definitely it's have been changed the landscape in the CubeSat and also the satellite business, because it has lots of attribute of a nice future that's including you being able to much easier to find a launch opportunity because you've been piggyback to a lot of launcher, and definitely that's also can serve as a very good platform for university and research institute, because we have been able to test and prove our idea, okay, in space. Okay, and this kind of standard definitely can find in the CubeSat data specification in the website, and in this a lot of test requirement and also a design requirement, internal mechanical and electrical requirement are there. So in the past 20 years, CubeSat are regarded as a disruptive innovation in space industry. And indeed, the market based on the CubeSat is also have a strong growth. In Taiwan, definitely we look into this kind of nanosat opportunity, and we've been associated UNISEC Global to try to promote this kind of activity. And we have established UNISEC Taiwan last year. And currently, the member including Tsinghua University and Central University and Tankang University. And we welcome other university and research institute join, so we could then promote this kind of, not only in the CubeSat, but also CanSat, but also some sounding rocket kind of activity, so that we could have all the human capability building and also try to looking for some international cooperation. And as I'm from NCKU, I would like to share with you some activity related to space in NCKU. And at NCKU, we have some sounding rocket program. We also involved in some microsatellite and CubeSat kind of activity that's including some microsat design and CubeSat design. And also the university has some test facility and ground station that can support all this. And to back it up, also we have some high balloon to do some experiment, as well as some curriculum that could do the human resources training. And in terms of CubeSat, which is the main subject of this series lecture, definitely NCKU have been involved in some CubeSat program. and that's including the PACE platform of altitude control experiments, and Phoenix, and also the Birdie, RSAT, and Iris. Okay, and you can see from the diagram, that's mean we've been doing this from the 2003, and some CubeSat program have been conducted. In today's presentation, I would like to share with you the Phoenix CubeSat, because it's one of the more complete and more comprehensive program that we had accomplished. And definitely we all keep the ball rolling. That's mean we are still working on some CubeSat activity. That's including the Iris CubeSat that's been designed. So the QB50 program is an European program, and it's an international program. The original goal is to have 50 CubeSats, and that's been designed and developed at a different kind of institute and internationally. And they would design this kind of CubeSat, but they would try to launch into the lower Earth orbits, or more precisely lower hemisphere, to do multi-point in situ measurements. And also there are some, this kind of data can definitely be useful for certain re-entry research. And it's a project coordinated by Montgomery Institute, and the time span is 2011 to 2017, and the budget, as you can see. So the overall objective of this program is definitely the in-orbit demonstration, and also facilitating for access to space, because that's what encourage a lot of university and research institute to build and the CubeSat and then launch into space. And with this, the serve also serve the purpose of education and scientific research. For the figure on the right, definitely you can see the lower hemisphere that we are talking about, for example, 100 kilometer to 300 or 320 kilometer altitude in the space. And that kind of altitude definitely is lower than the, for example, International Space Station, but much higher than what you can reach with high air balloon or sounding rocket. But the data there are rather sparse. And so therefore, if you can use a CubeSat to collect this kind of data in situ, that will also many good to build a model of this kind of lower hemisphere, and then definitely you will then be able to predict this kind of interaction between space and atmosphere. Although the original call for the QB50 is a 50 CubeSat, but eventually 36 CubeSat make it. That means eventually they launched 36 CubeSat, but if you look into the Montgomery Institute, they're talking about 38, because before this 36 CubeSat, there are two, that's mean preliminary, or the preliminary CubeSat that were launched for the validation. Okay, but officially there are 36 CubeSat that's been launched, and 20 of them was launched from the International Space Station, and 8 from the Indian rocket PSLV. And for this, you can also see the distribution international, different kind of country, different kind they have launched or participate in this kind of projects. NCKU have been involved with the QB50 program at the very beginning. That means starting in, actually that's mean in 2012 that we have been selected as a team member. So therefore we participate in the program and then follow all the coordination led by VKI. So for that, a lot of activity that you had to prepare. That's including all the documents and all the design and all the review there. Okay, so essentially in 2013 that we finished a preliminary design review, and 2014 that we accomplished a critical design review, and then we will then do all the assembly, integration, and test activity, and starting from 2015. And in 2016, we delivered this CubeSat to the launcher, and the launch was in 2017, and in 2018 we had almost 2-year operation, and 2019 is re-entry into the orbit. So this Phoenix CubeSat, the main characteristic is original mission life is 6 months, but eventually we have a 2-year kind of operation, and the orbit is launched into the International Space Station orbit. And it's a 2U CubeSat, and the payload is ion and neutron particle measurement units that developed by University College London. And we also, at NCKU, we design in-house a solar EUV sensor, because we think that if we can measure this kind of solar UV activity, we will then be able to get more data, and then hopefully that will also be useful in the analysis of the ion and neutral particle. Okay, and the CubeSat have a body mount solar cell, and the communication due to the frequency coordination, we are adopting UV band. That means it's a 9,600 bit per second for downlink. And the satellite, because the university satellite, so we adopt a lot of cost components, and some definitely have certain flight heritage, but a lot of cost components are there. And we also, there also is a ground station network for mission operation. So in our operation, that's not only NCKU ground station is involved, we also cooperate with some other ground station and then get the data downloading. And if you take a look at this CubeSat, it's a 2U CubeSat as mentioned. So it's all the subsystem as you could imagine. That means if you want to make a CubeSat, definitely you will have all the different kind of subsystem. That's including you have attitude determination control subsystem, you have onboard computer, you have electrical system and power system, and then you also have a telemetry system that's been doing the communication. And on top of that, you also have structure and thermal control. Okay, and for this Phoenix CubeSat, we have two payload. One is the ion neutral mass spectrometer, and that's in the flight direction. That's on top of this kind of figure. So there's a fish can, that means that there's a probe there, and underneath there's a certain circuit board that try to measure those ion and mass neutral mass measurements. And also, as you can see, certain circle kind of shape of plates, those are solar UV probe, and those are used to measure the potential difference, and then hopefully that will gain some knowledge about the solar UV activity. And the circuit diagram, as you can see, is here. So almost always you have to design and manufacture all the system, although we purchase some component from international market, but we have to be responsible for all the integration task. And so as you can see, there's an ADCS, EPS, onboard computer communication module, and also two payload that's on the right and left figure there. Okay, so you have this kind of ready, and definitely a lot of activity had to be spent on design the software. That's mean you had to design the software, try to integrate all the functionality of the different kind of module, and then make it work in space. And this kind of development takes some time, but so in this figure, you can see how the things going. That's when we start with certain analysis model, and definitely you try to look into whether it meets all the structure or mechanical kind of requirement. And then after that, we do the design, do the manufacture and assembly, integration, and all the tests. So this PowerPoint slide that shows some of the certain design, and as you can see, there are certain modules that are purchased from the international market, but there are also some modules that were designed and manufactured by our own self. And definitely eventually that you try to integrate them, and then check the mass, that's feed the, that's make sure that it meets the CubeSat standard. Okay. And there's a short video that's talk about the assembly, so I think it's nice to show. So as you can see, this is a short video, but talk about all the activities. That's how things have been integrated, and then eventually that's have been assembled into the CubeSat. So lots of circuit board, but before you do this, definitely you have all the book, do the planning. Okay. And we do all the tests from 2014 to 2016, so that takes some time to do the tests, because tests have been many unique experience, because different CubeSat, although they may follow the CubeSat standard, but all the tests will come out with different kind of issue there. So we take some time to do the test. That's including setting up the test equipment, and then make sure that the tests will meet the standard. And so a lot of tests was done there. That's including thermal vacuum, include mechanical, and then the shock test, and also the certain end-to-end tests. And afterwards, we delivered this CubeSat to Netherlands, and that was the final integration in Netherlands, and then they shipped it to Houston, and afterward to Florida, and then for the launch. And the launch happened in 2017, and then definitely it's launched from the ULA, and then shipped to the International Space Station, and afterwards it was released from the International Space Station there. And then just a typical figure there. Okay. And it was after it's released, definitely the task go on the NCKU side. So we managed to contact the satellite, and then read all the telemetry, and then send the telemetry command. And then we make sure that the operation can be done. And afterwards, we do a lot of operation, and you could see this figure there. And this video shows that the operation. And the unique thing about this is, although you can see a certain animation, but it was indeed recreated based on the telemetry. That's when based on the telemetry, that's recreate the satellite attitude, and then to make sure that the operation is as we planned. That means we've been able to control the attitude of the CubeSat, and then make sure that it's doing the operation, so that it can accomplish the 3x stabilization, and then collect the data as needed. So this, and the data, as you can see, it's including the IMMS and the solar UV data. And at QB50, they require each team to submit the data to the web, and then definitely we are one of the top provider internal data among. So this is the data, and as you can see, the TW01 is the code name, and then we provide a lot of data that's including the satellite telemetry data as well as the payload data. And if you talk about accomplishment, that definitely we are happy that we've been able to perform this kind of system engineering and international cooperation. And the data, I think, is mainly useful. That's not only in the payload data, but also certain satellite orbit data that's have been collected, and then that's useful for lots of research. And some of the team members eventually that spin up a new company that's called Odysseus, and they have been doing the space-related business ever since. I would then like to share with you some of the issues that we have all lesson that we have go through in this endeavor. Although, as you can see, we have been able to do something there, but in this process, we also learn a lot. And I would like to share with this because this may be even more important to learn. And we encounter some issue in the assembly, in the integration, and in the test. So I just bring out some issue that's maybe it's nice to share with you. One of the issues that's when we're doing the assembly is definitely we come up with a CATIA model, and then finite element model, try to look into, for example, mechanical property and all the information there. But when we begin to do assembly, we realize that there's an inconsistency of the model. Oh, it's a consistent model, it's just incompleteness of the model. That means for example, the side panel could not be closed. That's due to in the model we didn't take serious consideration of certain detail that's including the connector, harness, or even the certain groove. Okay, although this problem was eventually solved, and then you had to re-examine the sender. But it's always nice to know much earlier. But that's some issue that we encounter in the assembly. So that definitely we had to do certain fix to fix this kind of issue there. And also the completeness of model also related to, for example, there's a certain detail in terms of remove before fly, those kind of connector, and it's in the model is not complete there, and definitely that's makes when we eventually doing assembly, that's also has certain contact with the solar cell, and that's definitely can be mitigated, but that's the issue that we would hope that if the CATIA model is more comprehensive, then this kind of problem will not be happen. And also there's also issue related to the groove. Okay, so we purchase certain groove that's based on the recommendation from NASA. So that's when we purchase certain NASA qualified groove for this kind of, for example, solar cell. But it turned out that after some thermal cycling and vibration, we see that the groove become powder. That means the groove, the strength is no longer there. So that means we had to figure out what's going on. That means even certain product that's claimed to be qualified, but you really had to do all the tests before it's been included into the system. And in the integration, we also face a lot of issue, and we also learn a lot. And one of the integration issue is the software. That means we have all the system integrated, and definitely we do all the tests. And it turned out that certain time system is sometimes really tricky. That means you have different kind of processor and different kind of onboard timer, and then you have to make sure that you have a consistent time, so that we figure some time to resolve that. And also I2C is, which is interface between processor and certain interface, is also create a lot of issue, because I2C communication, you may get into a wait stage, and then you may wait forever. So that means if you do not have a good method to deal with that, your system may hang up there. And also certain memory is also is an issue. That means because sometimes you keep collecting data, but sooner or later, because the memory size in this kind of CubeSat is definitely limited, and so we may have to watch out for this kind of memory usage. You may have a many buffer full, and then all the system will then become nowhere. That means you just do not know where you're going. And also there's also the firmware version control, because you may have to control different kind of devices, and then sometimes this kind of version control need to be watched out, because this will come soon there. And during the integration, we also face some issue in the attitude determination and control. Okay, and in the figure you can see the system being integrated, and then with the PC doing the test controller, and through the EGSE we control the Phoenix CubeSat. But it's sometimes difficult to test the ADCS in a university environment, because we do not have many complete test fixture to do that, especially for those sensor and actuator. Although we managed to, for example, to check the sensor quality, but sometimes the actuation just cannot be do that in a many comprehensive manner. So it's many challenging there. And eventually we figure out some way to deal with that, but we have to say that we have to admit that it's was not really completed, when we launched the CubeSat. Although eventually it turned out to be not too much an issue in space, except that's maybe the temperature issue, but this is something that we figure out that can definitely have room for improvement. And during the test, definitely many challenges because we take more than 1 year to do the test. And we have all the test procedure ready and do the rehearsal, but it turned out that it's hard to go as planned because you had to be flexible because sometimes the test furniture, test equipment, for example, if you try to do the thermal cycling, and it may take much longer than you expected. So lots of things there. And on the right, you can see the detach of the antenna. So that's the picture that I took after the shock test. So that means after the shock test, you can see this. So that's, and we realize that it's over test, but the damage had been done. Although definitely we fix that, but as you can imagine, it's always many challenging in this kind of test endeavor. Okay, but eventually that we finish all the integration and all the tests, and we deliver that. But a lot of lessons learned through this kind of activity there. So as a short conclusion, I think CubeSat has become a de facto standard and opened a lot of window for space adventure, and a lot of people will get interested, and then it could be many important menu for space activity there. But the recommendation definitely you have to do that in a systematic manner. That's mean because after all, it's a space system. And so although in the finished design that we try to follow all the standard, but as you can imagine, a lot of issue may still pop up, but that's a part of the process. And we are lucky and we are happy that we've been able to do this, and it's been a successful case. But as you can see, also find out from my presentation, a lot of lessons that we have learned, and I think we are happy to share with this, and then hopefully that's everyone that we can then exchange this kind of experience, and hopefully for the next CubeSat that can become much better. And I would like to acknowledge all the students that have been involved, and a lot of sponsor and cooperator, and all the students that doing all the hard work. And with that, I thank you for your attention.
Thank you very much, Professor Juang. That was a very interesting insights at your experience in developing the first successfully launched CubeSat from a Taiwan university. Of course, I noticed that in your presentation, you mentioned that Phoenix was developed over the course of over 5 years, from inception to end of mission. And one challenge I always face at universities, especially for long-term projects like this, is how to ensure continuity in the project as students graduate. Did you have any particular way of ensuring that different specializations in your team were passed on, or various technical developments were not lost as students moved on and graduated?
Yeah, that's a many important question actually, and that's, I think every university has to face this kind of the issue there. That's in the continuation of the manpower, because most of the work are done by students, and students come and goes. So we try to make sure that the handover are there, and we try to make sure that the documentation are there, and we try to make sure that's critical subsystem someone can take over after some other have been graduated. So it's a challenging, and then it takes some time, because sometimes the university, the student come and go, and then even you may identify some student that may be able to be responsible for some subsystem, but eventually that's she or he may not be able to do that as you expected. So this kind of program is always there. So we always keep move one step forward and then one step back. So there's a zigzagging. So, but that's something that I think all the university, they face this kind of issue there. And that's also, I believe this kind of limitation can be compensated by organizations such as UNICEF Taiwan, because in this kind of organization that's across university, and then it's maybe easier to accumulate this kind of knowledge. And definitely TSU may also serve as a platform for all this. That means somehow we try to keep all the knowledge, and then anyone who need it, they can also find a solution. So that we may not have to start all from the scratch every time.
Okay, thank you very much. And on a related question, it's been mentioned in several of the talks today that oftentimes it's very helpful if students have mentors they can talk to regarding different specializations or particular questions, for example, regarding structures or electronics, someone other than the PI. Did you have some way of arranging for mentors for the students on your team?
Yes, that's because, for example, as you can imagine, a CubeSat can encompass different kind of disciplines. You have structure, you have thermal, you also need some software, you need communication. And at a university like NCKU, that we definitely have different departments. And so we ask for help for some professor at different department, and we try to establish certain links. So just in case students have some specific question, for example, internal control, he can at least have someone try to discuss with. So it may not be the totally full-time mentor, but definitely certain expertise can be shared from that menu there. Okay. That's our experience.
Very important. Are there any questions from the audience for Professor Juang? If you have a question, you can click raise hand below the screen. Wayne, did you have a question?
Yeah, I would like to, very nice talk, Professor Juang.
Thank you.
A related question about this transfer or transmission of experience, and you need to have things to go on, right? The working. So what is your upcoming project? I do have a project ongoing, so that you could keep the team intact or building it up.
Yes, that's indeed many question, because we try to keep the team, but we try to keep the budget. But sometimes the budget also come and go, and still come and go. So definitely that's many challenging in a system like Taiwan. Okay, but I would say we are trying to manage at the minimum manpower. That means we have certain systems set up, and we have certain markup or certain module there. So that means just in case new students come in, they can be much easier to learn. But it's always an issue. At a university, you always have the manpower issue. You also have budget issue. But we are at this stage, we are doing another CubeSat, and then we also rely on some former students. They have certain experience, so they could guide the new student, and hopefully that we can do that in a much smoother manner.
Yeah, you two main players on CubeSat in Taiwan on board right at this moment. I think it would be very nice if one could come up with a joint project. You two university groups could say work together on one single project, and then you do this and you do that, and then to learn from each other. Using that as an exercise. And would you like to do that?
Yeah, I would be happy to. And I've been talking about Lauren, but we try to look for the good opportunity and then good subject, try to mutually explore. Okay, so the door is always open.
Yeah. We're certainly open to collaboration. And actually for our next mission, SciOneX, we've actually been speaking with Professor Alfred Bing-Zhi-Chen about including his payload, which first flew on Phoenix on our spacecraft. And certainly, we're very happy to share our experiences, although, of course, we've only been learning about life on orbit over the past month. So I think we have a lot to learn from you guys.
Right. No, I think it's always good to cooperate, because in Taiwan, after all, is small. So that's we have to share, and then hopefully that's everybody can grow. Okay.
Mm-hmm. I mean, the sharing is not just exchange of payroll, but also in terms of the mission requirement, mission infrastructure.
Yeah, that I agree. That means the more in-depth kind of cooperation. Okay.
Certainly, if you need a ground station, we have one here, and I can guarantee you that one thing that comes out of IdeaSat is it will be brought up to full operating condition.
The problem is that John might not trust you,
Well, I did have another question, because over the past month, we've only begun to experience what it's like operating a spacecraft on orbit, and it's been a very nervous experience for all of us. Did you have any particular experiences with encountering anomalies on orbit when the spacecraft is in orbit, and how did you go about solving them?
Well, the operation is very challenging because the student have to work in the night shift.
Yeah.
But that's something else. And definitely the satellite may not go as you planned. For example, sometimes you may have the power shortage. Sometimes you may have certain anomalies in turn. So the system may be reset, and then you have to go over the procedure again. So that's all the process. Okay. So we did encounter those, but we managed.
Okay. If there are no other questions, then thank you very much, Professor Juang, for your time and for sharing your experience.
Thank you very much, and thank you, everybody.